this time we will hear what his daily job is, as he said just, not how his hobbies, which was the first topic. So it will be on BC of polaritons. And
okay. All right, you can turn that off, I guess, there. Okay, good. So actually, I'll show you my outline here. Just want to thank the experimentalists and collaborators here. Is there a laser pointer here, by the way? I think there is.
Switch, and you can use it for your slides as well if you want to.
No, I don't want to bother with that, but I do want to use the laser pointer. Okay, you guys can see that? Yeah, so my students deserve a lot of credit for the experiments that have been going on, obviously. And the sample growers are of great importance. And one of the things about doing solid state physics as opposed to AMO is that your sample is already there, all fixed. So you don't have to recreate the sample every time you do the experiment. So you go through a lengthy MBE process, but once you've got it, there it is, and now you're just analyzing it. So I'll come back to that. There is a connection to the stuff I talked about before, and this came up in the Q&A the last time I was talking. Are there nonlinear additions to Schrödinger equation, beyond just standard unitary physics? And I introduced sort of argumentation for that in my first talk for fermions. And then, the question came up about bosons. And it turns out experimentally there are interesting questions to ask about whether there's also nonlinear terms for bosons. So I'm going to try to reserve the last fourth of my talk for just those kind of considerations. But before that, I'm going to just do a quick survey of BEC, of polaritons. So I'm going to start at the very beginning because this connects to these whole non-equilibrium discussions. So I'm just going to introduce Bose condensation in a slightly different way from a lot of the time the way people see it, which is to think about it dynamically. And this is really reproducing Boltzmann's argument, which feels really good to be talking about Boltzmann's argument here in Vienna. So if we just do a detailed balance of some collisional process, we can write the forward scattering rate as proportional to the populations of the initial states. And that was written down already by Boltzmann. And then you have from quantum mechanics these final states factors where the plus is for bosons and the minus is for fermions. And then the principle of detailed balance is then to say, well, this should be a time reversible process, that the matrix element should be independent of which way time is running. And so we should be able to reverse this in equilibrium and say that the reverse process is just given by this, and these two should be equal to each other in equilibrium. And that immediately gives you a constraint on the form for the population. And in about 1 or 2 lines of algebra, you can prove that the only solution to this is occupation number of this form, assuming that energy is conserved, where the minus now is for bosons and the plus is for fermions. And so in just a couple lines, you get both the Fermi distribution and the Bose-Einstein distribution. But one reason why I point this out is because this helps you understand if you go away from equilibrium and you're not in perfect equilibrium, that this argument is not going to utterly break down. If you don't have true equilibrium, it's not as though you can't have quantum statistics and you can't have Bose-Einstein condensation. There's been a whole lot of theory of non-equilibrium condensates where you say, well, if this is not quite exactly true, then this is going to be nearly this and not exactly this, right? And so I'll come back to how we do that in terms of dynamical simulations.
Can you explain the scaling rate, why they have this?
Why they have the final states factors?
No, why they have exactly this expression, the scattering rates?
Why is m the same, or?
Yeah, I'm generally not familiar with this.
Okay, so this is basically just Fermi's golden rule in a many-body system. Okay, so you basically just have 2 pi over h bar times m squared is just coming from Fermi's golden rule. And then actually, it always feels really good to do this, but it's worked out in my book in chapter 4. If you didn't have quantum statistics, you would just say from Fermi's golden rule that you would have these first two factors just because the input states are proportional to those numbers, right? But then anytime you have a transition on a quantum state, you've got the square root of 1 plus n, right? And since you square that in Fermi's golden rule, you immediately get these 1 plus or minus n factors there. So, I mean, one nice thing, way to think about that is, you know, in one line, you see you get Pauli exclusion for the 1 minus n, and you also get stimulated scattering for the 1 plus n for bosons. So it really just comes out of what you're putting in for the commutation relation. So then the experimental prediction of this is simply plot this in equilibrium, and you get the occupation number as a function of energy. And if you plot the occupation number on a semi-log plot, then the Boltzmann distribution is just a straight line. Then you see that the increasing density gives you an increasing chemical potential, gives you an increasing peak here. And in 3 dimensions, this will actually go to infinity. In 2 dimensions, it never goes purely to infinity, but you still get something very peaky in your system. And so you can still talk about a condensate. Yeah.
On the previous slide, these scattering rates, you're not assuming any particular form of the interaction. There's no restrictions whatsoever on the interaction, or is it just for specifically like full-body?
No, it's really true for any energy-conserving interaction. All right, so the things that go into this are detailed balance, which is an assumption in equilibrium, and then the other is simply energy conservation, because you see, you basically have an e to the something here with an energy in it, and so when you multiply e's, you add the exponents, which leads to adding these energies together, all right, which means that the energies up here and the energies here have to equal each other, which is the same as energy conservation. So this is a very general rule. It's little, if you go back to Boltzmann's arguments, it's how he argued, right? He argued from detailed balance. But in his case, he was treating these as probability factors, whereas these are now expectation values in quantum mechanics. And again, that comes out of the Boltzmann equation derivation. So now I'm going to talk about polaritons. And probably the easiest way to think about what a polariton is just start with photons, which are good bosons. And now we're going to go into a medium. And one of the nice things about solid-state physics is that you can create like alternate universes in solid-state physics, right? So if you want an electron with 0 mass, we can give you that. If you want an electron with fractional charge, we can give you that. You know, if you want a one-dimensional or two-dimensional universe, we can do that. And so we can also give you photons with mass, and we can make photons that repel each other. So, you know, you have a lot of things to play around with. So the tricks here are we're going to start with photons, and in this medium, we're going to give them an effective mass. We're going to give them interactions to repel each other. And we're going to put them in a mirror box, essentially, so that we have approximate number conservation. And under those conditions, then, they obey all the same equations as atomic condensates. You simply have a number conserved system of particles that are bosons with mass. The difference is if our mirror box is not perfect, then we're going to have weak leakage out of our mirrors, and we'll actually be able to monitor that, and that's going to be our data. We're going to see the leakage light, and that's direct in situ data for us. And so that's, you know, one nice thing about the polaritons. There's, you know, several drawbacks, but, you know, one of the nice things is that you can do non-destructive experiments all the time. You don't have to annihilate the thing in order to see what's going on. You have a continuous leakage of the light coming out of the mirrors. All right, so just to start at the very beginning with excitons, polaritons come from mixing excitons with photons. So excitons, to go back, you just think about it as a quantum of excitation. It's an excitation of an electron. And so if you think of a solid as a bunch of atoms, we've got some kind of energy gap, and we're going to kick up one of the fermions into an upper state. That can then move around now that it's in this mostly empty band. But you see that if it moves over here, we have a net amount of charge. And so there's going to be a Coulomb repulsion from that region. So that's going to tend to kick other charge away. All right, so one of these bottom level valence charges can move away. But if you just sort of invert your thinking, you can think of that as a hole in the valence band that was attracted to this region. All right, so in the whole picture, we say that we have an electron in the excited state and a hole in the bottom state, and those are now attracted by a Coulomb attraction. And so this is now one complex which moves together, which we call the exciton. Now, why do we want to mix these things? Because we get now a very strong interaction. You can't put two on top of each other. If I made two, right, I can't put this exciton on top of that exciton because that Pauli exclusion says I've got two occupied ones in the same place, right? So there's going to be a hardcore repulsion of these things, all right? So if I mix photons with excitons, I'm going to get now, in optical terms, a very strong chi3, but you can just think of it as a Pauli exclusion that the two can't sit on the same spot together. All right, so what the structure is then is the following. This is one monolithic device. So we have mirrors. So as I said, we have a mirror box, and typically it's planar. So we have freedom of motion in the, along the plane, and then we're restricting in the z direction. Then we're going to put excitons in these active layers here at the antinodes of the confined photon. And then these spacers are transparent solid also. So the whole thing is one solid device. As I was saying, you know, this is a nice big project for an MBE grower. But at the end of the day, once you have it in the experimental lab, all of your optics is to look at it, not to make it. Yeah. Molecular beam epitaxy. So this is literally growing structures atom by atom. So you're essentially doing it like a cake. So you have a substrate, and you're simply shooting a vapor of atoms, but you're doing it very, very slowly so that you're getting one atom layer deposited at a time. And they actually have ways with X-rays to count how many layers they're adding per second. All right, so they can literally see a meter going up and down as you get one wetting layer, one atom thick. So it's very impressive. And it leads to extremely high resolution structures. So in terms of solid state physics, Lauren Pfeiffer, our collaborator, has the world record for mobility of electrons, of just the quality of the structures, because you want low disorder for all of these things. And it's funny, he never got the Nobel Prize, but he was a co-author with 3 different Nobel Prize winners in the quantum Hall effect, because he made the structures that they were using. Okay, so if you look at the dispersion here, the exciton, to all intents and purposes, is just a constant energy gap for the excitation. And then the photon has an effective mass, and I think I have an equation for the photon. No, I guess I don't. Essentially, you can see that there's a confined mode, so there's a minimum energy for the photons, even at k equals 0. So this is k in plane. And then there will be dispersion for that. And so the photon all by itself has an effective mass. And that just comes from the constraint, the fact that we've got a minimum mode that it's sitting at here. And so if we now think of this as a two-dimensional system with freedom of motion in the plane, all right, then the three-dimensional photon has become a two-dimensional object with an effective mass. All right, now these two couple to each other because a photon can turn into an exciton. The photon can get absorbed, stay there for a while, then re-emit a photon. And so if we turn on the coupling, we get this dispersion, which is now, these are the new eigenstates, and we're going to call this the lower polaриton and this the upper polaриton. And now if we look at this, it retains that extremely light mass that I was talking about, but it also has excitonic character, which means that they're repelling each other. And so a simple picture of this is simply viewed as a two-level system where you have the photon and the exciton energies, and you're going to diagonalize it, and so it's going to be some fraction photon and some fraction exciton. all of these sort of nonlinear properties are coming from being mixed in from this excitonic part that we're putting in. Now, you may ask, why are we doing this? One of the main reasons is just effective mass. If you just go back to very first principles ideas, quantum effects generally become important when the distance between the particles is comparable to their wavelength. And then you can't tell two particles apart. So if I just do unit analysis and get an average distance between particles in terms of the density and an average wavelength in terms of the temperature, I can turn this around and get a temperature as a function of density, and it's inverse with mass. Okay, so that means that light particles undergo quantum effects at much higher temperatures. Now, what is the mass here? The mass of these polaritons is about 10 to the minus 4 electron masses. Right? So think about it, we're talking about 1/10,000th of an electron. An electron is 1/2000th of a proton. And a typical atom may have 200 nucleons, right? So this is very, very, very light, but not zero mass. Room temperature condensates of these are routine now, actually. Now, equilibrium ones are not, but at low temperature, we can get equilibrium condensate actually routinely at this point. And by low, for us, is like 20 Kelvin, as opposed to for atoms, where you're talking about like nanokelvin, typically. So we've raised TC like 9 orders of magnitude, effectively. All right, so just some details here. We have all kinds of ways. So, the first 10 years of this field was just doing a lot of trapping. And so I'm not going to go into a lot of detail, but there's lots of ways to control these to make traps. So we can use laser trapping, and we can also make static traps. And all of them have sort of advantages and disadvantages. I'm really just going to talk about, for sake of time, one of these, which is the effect of shifting the cavity. So if instead of having a cavity which is flat, we put a wedge into it, then the photon energy is a strong function of the position of the cavity. So if I simply look at this wafer over here, I have one photon energy because the cavity is wider, and over here the cavity is narrower, and so I have a different photon energy. And so at some point on the wafer, these will cross through each other. And we'll have that same anti-crossing I showed you before in momentum space. Now we have it in real space. What's nice, this really does two things for us. One is we can pick the exciton fraction just by where we look on the wafer. So if we work way over here, it's mostly just like photons that are non-interacting. If we work over here, it's mostly like excitons with high mass and strongly repulsive. And we can sort of tune anywhere in between there. But the other thing we can do is simply use this as a force, right? So this is a gradient of energy as a function of position, right? Well, that's called a force, right? So it literally means if I put polaritons, if I pump light into the system here, they will feel a force pushing them to one side to go to lower energy, right? So we can use this effect in various ways to manipulate these things and move them around. Everybody clear on this? Okay. So I'm going to show you a cute experiment that has nothing to do with condensation. Actually, I'll give you one more detail before I do that. I talked about the leakage light out of these. So the leakage light coming out obeys Snell's law. So if we think of the polaritons as having a given momentum in the plane, there's going to be a one-to-one mapping of that momentum to the momentum of the photon that's leaking out at the end of the day. So you can call that a generalized Snell's law. So what that means is if I angle resolve the emission angle of the photons, I immediately get a momentum distribution for my particles. So just by looking at this thing, I can take just a microscope lens and spatially image and get the spatial distribution. But I can also then do angle resolve measurements, and then I get the momentum distribution for the same thing. So literally in the lab, you simply do a flipper mirror to go between real space and K-space with these things, to directly see one or the other. Now, the same rule works with time reversal. So if I have a laser coming in from outside, I can inject at a given angle and create polaritons with a definite momentum. So I can inject them exactly at the momentum that I want. And that leads to a kind of cute experiment here. Here we've got a wedge in the cavity, which, as I showed before, effectively corresponds to a gradient of potential energy. The ground state energy is shifting. And I'm going to inject them with well-defined momentum, and they have an effective mass. So the whole thing translates to a ballistics problem, right? You simply are saying, I've got, freshman physics. I have a particle moving uphill in a gradient, and it's got a certain amount of kinetic energy from the start. So what's going to happen? Well, it's going to give up all its kinetic energy at some point, turn around, and go back the other way, right? So we can do this with time-resolved measurements, and this is actual data now where we see this, right? So we're firing photons in, and it's kind of cute if you think about what's happening is the photons are going in, and they're not hitting anything, they're just turning around and coming back the other way, right? It's actually completely just from energy and momentum conservation, right? It's just the same as your classical ballistics. But because we've given these photons an effective mass, then that, they obey that, and we see this nice parabola. This is just literally just the parabola for a ballistic particle. One thing this shows us, this type of data, though, is the quality of the structure. So these polaritons live for hundreds of picoseconds. So you have to think like an optics experimentalist here. So a femtosecond is fast, a picosecond is a normal amount of time, and a nanosecond is t infinity, right? So, t infinity. So these things live for effectively t infinity if they go hundreds of picoseconds, because we can resolve them on single picosecond type timescales. Yeah.
Can we talk about the photons being? There's this classical image given about sort of all over the hill. Is the photon, while it's inside the material, that well spatially localized? When the idea, I guess, of calling it like a polariton is that it's no longer really just a photon, it's some sort of composite mixed dressed
Yeah. Mm-hmm.
state somehow. So I'm just out of curiosity, is this still a sort of meaningful notion of a photon?
You can create a wave packet. So that's essentially what we did in this experiment. There's a laser here which has a well-defined radius of focus, right? And so that creates a wave packet of these things, which is a coherent wave packet moving. And so the size of the focus of your input laser defines the size of that wave packet. And so then when you look at these ballistics things, you can see that's diffusing out. So it starts out, if you take a slice in the vertical direction, you're getting an effective size for that wave packet. And that's smearing out as time goes on because of just diffusion. But it's still well sort of localized compared to other things.
But I guess this kind of size of the phase space, if I compare, is much larger than each bar. That's why Pearson has a kind of checker. So it goes grading in a kind of classical.
Yeah, so you could, in principle, do a transform limited pulse where you would say that the position and momentum were both as small as possible, right? We're maybe a factor 2 or 3 away from that. We're not working really hard to make it a transform limited pulse. But in general, you can make a wave packet of a certain size and momentum distribution, right? And it would be localized, in both real and momentum space.
I guess my question is more about sort of the identity.
Yeah. Well, this gets back to the whole thought of particles, which I talked about in my first talk, right? What you can say is it's a well-defined eigenstate of the system, the polaritons, and so whatever you think of photons and whatever you think of electrons, what's no different here, right? So what I would say is, with a photon, there's no intrinsic length scale to it, but I can always make a wave packet of any size that I want by superposition, through Fourier transforms, right? The same is true of excitons and electrons as well. Yeah, there's some funny stuff. One reason why I wrote my textbook is there's certain things that get said in solid-state physics that are just not true. And one of them is holes don't exist in real space, they only exist in momentum space. I've heard that from numerous people, and it's nonsense, right? If it exists in momentum space, you can always make a wave packet of it in real space, right? It's not like holes don't have some reality. So I can say I put a bunch of holes right here in my solid, and there they are, right? That's a perfectly good thing to say, right?
I'm just wondering if there's a notion, if it's
Yeah, no, so you have to be careful. So if you say, if I'm doing a measurement of polaritons, right, then when I do that measurement, it will definitely tell me where both the exciton and the photon were, right? But I could ask a different question and say, if I have a polariton in an eigenstate, or say in a wave packet, what is the distribution of probability of where that photon will be? And the answers will be of the order of the wavelength of the light, which is typically of the order of microns, right? So it's generally delocalized, but if I do an experiment on position, then I'll, of course, find it in some place, right? Okay, so I'm going to run through fairly quickly some of these results. So first of all, when people started doing these experiments, we had very short lifetime, and so we did not reach equilibrium. But that led to a whole branch of theory on non-equilibrium condensates and non-equilibrium thermodynamics generally. And so just to orient you toward these, generally when people think of condensation, they think of sitting at fixed density and dropping the temperature below a Tc. For these experiments, it's far easier for us to fix the temperature and then just turn up the laser power to increase the density. So we're going to talk about a critical density that you go above for fixed temperatures, typically the way we do our experiments. So we make a trap, and we, as in cold atoms, expect then the BEC to be in the ground state of that trap, which is a localized distribution. And here is now very old data. This is a 2027, that's 15 years old. Thermal cloud in the trap contracts as the density goes up. Condensates look like they're counterentropic in a lot of ways, right? Because you turn up the pressure and they get smaller, right? Because the higher the density, the more they want to go into the ground state, which in a trap is a smaller state. So I'm turning up the density and the pressure, and it's reducing in size. Weirdly counterintuitive. At the same time, as I said, we can measure the momentum distribution. So if we do that same experiment, looking at it momentum space, we see it's broad and thermal in momentum space, and then narrows up becomes a very compact in K-space. And also, if we take a slice in energy, this is now spectrally resolved, so we can see the energy. This is just that parabolic energy I was telling you about. We can see now there's line narrowing. It's very coherent, and that's an indication of the coherence of the system. So again, if you think about it, okay, it started out broad in real space and broad in momentum space, and when it condensed, it got narrower in real space and in momentum space, right? That's possible because when we started out, we weren't transform limited, right? It was broadly disordered. And then as you get to a condensate, the condensate actually approaches a transform limited state. And so you're actually getting now to the size of the ground state will tell you what the size, in momentum space will also tell you what it has to be in real space, right? Just by Fourier transform. So we could fit these distributions, and when you first look at these, you say, well, this is great. This is exactly what I predicted before for the Bose-Einstein distribution, which is, straight line at low density and then a peak in the ground state, which appears. This is indeed, you can do coherence measurements and see this is coherence. So this is really an onset of condensation. But a little bit more analysis shows that these curves do not fit that equilibrium Bose-Einstein distribution that I was showing you before. And that's because in these early experiments, they had fairly short lifetimes. So the lifetime in the system was comparable to the time to thermalize. And so they ended up having a much higher tail. So if I actually tried to fit this, if I fit the low energy spectrum, I could fit that to a Bose-Einstein distribution, but I have too hot of a tail. And this tail fits a temperature that is not the same as the temperature of the low energy states. So that led to a kind of a lore that still persists in the literature, which is that polaritons are somehow intrinsically a non-equilibrium system. You'll see, like all the time, people say polaritons are intrinsically a non-equilibrium system. That's not the case. It was the case for these ones because they had short lifetime. But if I make the lifetime longer, then I would expect to reach equilibrium. So it's just a matter of lifetime compared to thermalization time. But in that sort of period there where we were all looking at these types of systems, a lot of theory was done, and this is that same Boltzmann approach. So this is now the full quantum Boltzmann equation for two-body scattering, again with these final states factors. And you can see a lot of theory being done on this. Again, where these are all now quantum expectation values for the average occupation for a given case state. And you get very sophisticated. Some of the stuff we did incorporates all the background photons and background electrons and other things you expect in your system. And what you can find is, indeed, you get very good agreement. So the green curve is a fit to the actual data, which fits quite nicely. But then in your theory, you can do interesting things. Like you can simply turn off those 1 plus n factors, right? So I can't do that experimentally, but in the theory, I can simply comment these out of my code, right? And if I do that, then I get the blue curve. And I never see this peaking up in the ground state. So that peaking up is very definitely related to the quantum stimulated scattering, which is really what leads to Bose condensation. So then we can think about this as sort of 3 different regimes. And I'll just go through this very quickly here. I want to move to now, in the last 5 or 6 years, maybe even longer now. I think the first paper came in 2015, which is already 8 years ago. Time flies. But we now have samples that are much, much better. And all, quote, that it required was getting the MBE people to make higher and higher Q. So typical structures had Q of 5,000. We're now looking at Q of 300 to 400,000. So that's like a factor of almost 100 more in lifetime in some cases. And so now we get thermalization, right? So we get these particles to live much longer. Now, simple in concept, but experimentally it means that you have to have your MBE atom by atom growth be stable for 30 hours for one sample. So it's asking a lot from an MBE person to say, can you dedicate like a whole day? And if anything changes, you have to throw that one out and start again. Somewhat heroic. But the nice thing is, if you get one that works, now it's a solid that just sits there, right? And so you can use that over and over and over. And so now, as I said, we have lifetimes that are nearly infinite, i.e. a few hundred picoseconds. So with this now, we can make an optical trap and collect them and look for equilibrium. And I think I'm going to skip the details for the optical trapping for sake of time and just go right to the punchline, which is that we get really nice fits now to this Bose-Einstein distribution. And you can see at low density, again, basically a straight line, which is thermal. And then it's peaking up. And these are absolute numbers. These are not relative numbers, but this is the actual occupation number per state, something we can actually measure from our optics. And there's some uncertainty in the overall scale, but the relative occupation number is fixed by the experiments. So you can see now that we're getting nice fits, nice equilibrium in this case. But something, this was 2017 already. If we go to higher density, so you can see this is occupation number of several per state, but it's not thousands like you would expect for a condensate. When we get into the true condensation regime, something bad happened. We moved away from equilibrium, and it turned out the reason was because it was becoming spatially inhomogeneous in the particular type of trap that we were using. So that was 2017. I have a really bright student who revisited these experiments and did actually experiment with no trapping. Sometimes simpler is better. Just took a very powerful laser, defocused it to make a really big, broad, homogeneous cloud, and then just use a pinhole to look at the center of the cloud. And so it's very homogeneous in the center there. And you don't have to do with any deal of the details of the trapping potential and all the extra complications you might get. So when you do that then, this is sort of an experimental detail. You can then, this is raw data for us, right? So this is Energy is a function of momentum. If you're a many-body theorist, you know this is called the spectral function, right? So the number of particles is just given by the integral under this curve. So it's funny because for people in cold atoms, it's hard for them to wrap their minds around. The spectral function is data for us. It's not a theoretical construct. Like, it's actually a measured spectrum for us. And so from that, we get now these very nice equilibrium distributions all the way up to hundreds. And actually, he's done more that pushes it up into the thousands. So we have a condensate now of several hundreds to thousands of particles in the condensate. And it fits perfectly the equilibrium distribution all the way. So it's simply not true anymore to say that polaritons are intrinsically non-equilibrium. It just depends on the lifetime. If you push the lifetime up, you can get them to equilibrate. And then this is a fit of the chemical potential, just showing it moving towards zero as it gets into the condensate regime. Now, some of the things that relate to the last part of what I'm going to talk about is we now can do coherence measurements just by in situ interferometry. So we're looking at the leakage light coming out, sending it through a Michelson, and one of the arms has a flipper that basically reflects the image left-right. So we're superposing the image with a copy of itself flipped the other way, right? So that gives us interference measurements. So in this case, we're doing fringe visibility as a function of momentum. All right, and so again, when we don't have a condensate, it's incoherent. And as we turn up the condensation, we see it becoming nicely coherent. And now we can extract data from this by just measuring the fringe visibility as a function of momentum. All right, so if we plot that, then you see, again, just taking a slice through that and getting the visibility, which tells you then the coherent fraction. And so now it gets weird because everybody debates about two-dimensional physics. The three-dimensional condensates, have been done since like the 1960s. But even what you call the condensate in 2 dimensions is like kind of fraught, and people debate about it. So what we can say is the coherent fraction is well-defined experimentally. Whether you want to call that a condensate or a quasi-condensate or something else. So you can prove in 2 dimensions you cannot have infinite long-range order. But all real experiments, of course, are finite in size, right? And so what we get is a coherent fraction, which I would call a condensate fraction, as a function of density. And so as you move through the condensate transition, you see it's not a sharp transition, but there's a turn on of the coherence until you get up to, actually at high enough densities, you can reach nearly 100% coherence. Now, theory is actually lagging behind. So the theory, this is the best theory we could find. It looks kind of similar, but if we actually put units on it, it actually does not, it only matches our data for this region, and it goes haywire at lower densities. And so there's a need for theory to be able to predict what's going on right at the transition region. So it's actually kind of tricky. Now, I'm moving kind of quickly over these experimental results, but this is another just cute one where we can now make a ring trap. So this is a Mexican hat. So we've got a optical trap now with a ring and a peak. And there's a trench. You can't really see it in this resolution, but there's a trench here which allows the condensate to be in a ring. All right? So now this is a real space image of that. And so now we can do interferometry the same way. And if we do interferometry, we see a fringe pattern which says that this side of the ring is coherent with that. In other words, it's a single condensate in the ring all the way across with nice coherence. But we can do better than that. For a condensate, if you remember helium theory from whenever, the gradient of the phase is the velocity of the condensate. All right? So if we go back to helium theory, the velocity of the condensate is given by the phase gradient. Right? That's true for any condensate. It's just done by taking the gradient of this. And so that immediately leads to quantized circulation, because if we say, well, the wave function around any closed loop has to come back to where it started, plus or minus 2 pi, right? Because it's a single valued function. That then immediately gives me a constraint that the loop of the velocity around any ring can't just have any value, it's quantized, right? And so this is the textbook argument for while you have quantized vorticity in helium, while you have quantized magnetic field in superconductors, because when you have a single valued wave function, you have to have the wave function be the same, when it comes back to the same place, it can only have shifted by 2 pi radians going around any closed path. So that means that the circulation is quantized. Well, interference measurements directly measure phase, right? That's what we're doing with those. So we can immediately see the phase circulation of our condensate. So this is all theory here. This is density profile, phase profile. This is our predicted interference pattern. And then from this kind of data, we can Fourier transform it, erase essentially the lines, and be left with just the phase gradient. And that gives us what's called a phase map, which shows, you can see the phase winding around this ring. Okay? So if we do that with real data, we indeed get that. And what's cute in these most recent experiments is that on demand, we can start with a non-circulating condensate, give it a kick, and cause it to circulate. And it circulates that way forever until we come in with another laser pulse or until we turn off the experiment. So we can get now on-demand persistent circulation in either direction around the ring just by giving it a kick of momentum. This just shows the persistence again. It lasts for 14 nanoseconds, which is an infinite amount of time when the lifetime of the system is 100 picoseconds. One way to think about that is the average speed is a micron per picosecond, which means it takes 800 picoseconds to go around a 50 micron ring. And that means it's going about 20 times around within the amount of time that we can measure. I won't go into these details, just talking about how we generate this. Just kind of a cute thing is, in principle, we can put our ring into a superposition of both left and right circulation, just like you can with a superconductor, all right? And we should be able to pick that up with an interference pattern. So we can, with our interferometer, tell the difference between a stochastic fluctuation between sometimes being left, sometimes being right, and literally being in a superposition of the two, because they give different interference patterns. This doesn't violate anything because there's no measurement of which way it's going, right? So just like in a superconductor, you can say, I know it's in a superposition of both, right? Here I can say it's in a superposition of both because I'm not looking at the information of whether it's in one or the other. I'm only looking at the information of whether it's in a superposition, all right? So if I'm in this interference pattern, then I say, now I've got a superposition, but I can't say at any given point in time which way it's going, right? So this is a cute thing. We have not achieved this experimentally. But in principle, if you could do this, then you can make qubits of these things just like you can with superconductors. All right, so in the last 10 minutes or so, let me just talk about the theory of Boltzmann equations. So Boltzmann equations have an interesting history. They were already being written down in like the 1980s, if not earlier. Essentially, it's just sort of generalizing Fermi's golden rule and just saying, well, we're going to have a Fermi's golden rule for every possible transition in our system, and then just add up with an integral all possible transitions within a gas. And so this is your matrix element, energy conservation, and again, these are all expectation values. So I started using these way back in like the late 80s, early 90s to model data that we actually had. And then as I started thinking about it, it's like, it's actually not well justified in the literature as to why it should work. And so I went back and revisited that a few years ago. But let me just show you, first of all, some of the stuff that goes way back, right? So as we were talking about the other day, interestingly, you run this, there are no random variables being picked. You simply have a deterministic algorithm that iterates your expectation value distribution as a function of time, basically a density matrix. And deterministically, you evolve toward equilibrium and you stay there forever, right? So this is basically just equal occupation up to a cutoff. After some period of time, it reaches equilibrium and stays there. That's theory. This actually addresses a real, question.
You say deterministic, you mean it's a deterministic differential equation, but for the mean values of the numbers, not for the distribution. I mean, there could be different
Yeah, so what I'm saying is basically a numerical fact, which is if I have an algorithm, right, in which I input an input distribution, which say this one, okay, and then I iterate that algorithm, I proceed forward in time without ever picking a random number, and I get this, right?
But you iterate a number which the meaning of this is already a mean value of the number.
Yes, because what I'm integrating is this, right? So this is a deterministic equation for this, right? Which is essentially a reduced density matrix. It's the diagonal terms of a reduced density matrix, right? So I mean, it's sort of like, it's still interesting to me to say that like the density matrix, reduced as it is, evolves deterministically in time, where we're essentially just looking at the diagonal terms of that density matrix, and so it just continuously evolves with no, and of course, again, it's not all the information of the system, but then it gets into say, well, how, like, where did we lose information? Like, where did, you know, like, how does this work? You know, and I'll come back to that. But the other interesting thing to me was just like, KB is never input into the equation anywhere, right? You know, like, you know, there's no Boltzmann assumption, but you still get a well-defined temperature, and it really just comes out to that this has some average energy, right? And average energy is equal to 3/2 kBT. So essentially, it provides a definition for KT or KB, which is the ratio of the KT to average kinetic energy. All right, so this is experimental, way back. But we were already good at doing picosecond measurements back then. But what's cute about this is now the data is the dark lines and the theory is the dashed lines. And again, it's completely, the dashed lines is now iterated, just deterministically solved Boltzmann equation with no random numbers, and it perfectly fits the experimental data. And all later times, this is a Maxwell-Boltzmann distribution that just stays that way, and eventually the density drops off. So they work, right? So Boltzmann equations work. And there's the review article I think I referred to somewhere that, you know, actually, you know, you can do measurements showing things going toward equilibrium.
Sorry, and experimentally, how did you get 1 point of that? Because this 1 point is a mean.
Yeah, so what we're doing is it's similar. So it's similar to the experiment I showed before, where we're passively collecting photons, and we're doing spectroscopy. So we're getting an energy spectrum, and then you can do that as a function of time. All right, and so now you simply just sit and collect photons until you build up enough statistics to have a good, you know, square root of n for any given energy channel. Right. So this is a repeated experiment, right? So you're repeating it about 1 million times a second. Each time you collect maybe 1 photon from each pulse, and then you wait for a couple minutes until you've built up millions of counts, and you build up statistics that way. Okay, so Boltzmann equations show irreversible evolution toward equilibrium, and also very cute. There's an appendix in this paper, and also in my book. You can just use the Boltzmann equation to prove the H theorem at the same semi-classical level as what, you know, this 1 plus n's do. Okay, so what we did about 10 years ago, I was visiting Steve Gervin. We said, well, can we really justify the Boltzmann equation from first principles and not just sort of slap it down as many people do? And so if you go all the way back to your many-body physics and say, really what we're calculating is the change of the expectation value as the wave function changes in time, right? So we expand out a perturbation series, all right? And then we say, what are all the terms doing, all right? And then say, do I get out of that, you know, the terms that I want, and what assumptions are needed in order to get the Boltzmann equation out of this approach? And so I won't bore you with all the details. So here's one thing. If I start with an actual Fock state, right, then actually the quantum Boltzmann equation is exact, right? So because it's deterministic, you know exactly what your initial state is. What happens is, as soon as you iterate it slightly, your Fock state is no longer a Fock state. Now it's a superposition of a bunch of Fock states. And so the next time you apply the Boltzmann equation, it will be an approximation because your state is no longer a pure Fock state. So if you assume it's a pure Fock state, the quantum Boltzmann equation is exact. But of course, it's never a pure Fock state except if you force it to be so, right? Because as soon as you iterate even a little bit in time, you get all kinds of superpositions. But interesting things happen. Essentially, the bottom line is that when you do that expansion of all these second order, third order perturbation terms, you get terms that appear like this, where the one of interest, was rho of just, just the average expectation value of n, right? But the expansion generates all kinds of correlation functions like this. So you could call this sort of a higher order density matrix term, right? So this is a 4-order correlation function where all these 4 momentums are potentially different from each other. Essentially, the Boltzmann equation corresponds to setting all these equal to 0. Right? If you do that, you just get the Boltzmann equation very straightforwardly. Yeah.
I understand that this builds up these off-diagonal elements that you discard then, and that's why it's not unitary.
Mm-hmm.
Probably you call this also not unitary.
Right.
When I think about mathematically, at the beginning there was a differential equation.
A what?
You said, when I think now, not physically,
Right, yeah.
and I don't think about what in the unitary, let's say in the real, with the unitary evolution will evolve. But I think just mathematically your differential equation at the beginning, you said it's deterministically
Yes.
evolving this, and why it's not mathematically reversible? Is it like, why instead of initial condition I cannot have final condition and solve the differential equation?
Yeah. No, actually, the Markov approximation doesn't matter, it turns out. It's interesting because there was a whole other branch of physics done by people like Hartmut Haug in Frankfurt. It turns out that if you assume that you have sort of quantum memory kernels, like all that does is give a bunch of oscillations. But if you run it long enough, it always still becomes deterministic. So like that actually isn't the reason why you get irreversibility. It really is the fact that we're constantly throwing away phase information. So,
I'm not asking about that.
yeah, no, I understand your question. So if you say, okay, if the only information I keep is essentially the diagonal elements of the density matrix, just average expectation of any given K state, what's the occupation of that K state? And I now put that into my differential equation, right? That will always evolve toward equilibrium and will never reverse, right? So what that says to me is that the diagonal terms do not carry enough information for time reversibility. So essentially, the Boltzmann equation has built into it decay. So even though it's totally number conserving, the Boltzmann equation, keeping only diagonal information, is like an exponential decay type equation, where you see one-way evolution.
Does it mean mathematically if I put then in this equation differential t goes to minus t, it would not be deterministic?
No, it would still go to equilibrium the other way. Yeah. Yeah. No, actually, I have a little diagram I didn't put in this talk, but in my book I have a little diagram of like you go to an exact solution, and then you truncate all these phases, you kill them, all right? So now you have an approximate solution, and now that approximate solution would be time symmetric. It goes the same way either way, but it becomes a bad approximation of the reverse time, and it's still a good approximation of the forward in time one. So it's very tricky to think about what's going on.
Okay, but then you're saying that the differential equation is time symmetric, but it doesn't correspond to the physics.
Yes, yeah. So the difference equation is
That's what I was confused with.
well, yeah. So yeah. So you wherever you start. So if I go to this, case here, right? If I started with this, I always get this, and it never goes the other way, right?
Physically, in the experiment, so to say.
No, well, in the model. So the model will never go from this to this. The model will always go from this to this. And if I put this in, it'll stay this way forever, because literally every calculation becomes.
Which is the previous slide, I think, and
Yeah.
t goes to infinity, until t goes to minus t. Can I do that? Then this equation will, given the final state, will transform me into the initial one, the previous one.
No, it won't. It's weird.
It's many to one, right?
So,
whether this equation, I know that.
so the only information that goes into this is this function n of k, right? And if I run this, as I calculate this, okay, at each step, it's going to give me what the change is going to be to get the next one, right? And so that is it has an arrow of time. It's forward going, right?
You throw away these correlations, right? As you put them next to the arrows.
Yeah.
I don't even know about these correlations.
Yeah.
I say this is the world like that.
Yeah.
Now I ask myself, okay, I give initial state, I go, well, this is the set. And then
Right.
I say, okay, let's try to, with this equation, I have no knowledge about quantum mechanics.
Yeah, yeah.
I have a final state, and I go with the equation which is this one, but t goes to minus t. Whether I will get the initial one or not, that's why my question. This is 1 to 1.
Yeah.
And it's 1 to 1.
So I think the answer to that is if I'm at the t infinity limit, it will not, because all these terms go to 0, like they all cancel. It's a detailed balance. On the other hand, if I'm somewhere in the middle, then I think the answer is yes. It has an arrow of time. And so if I reverse it, then I think it would go backwards.
Okay, but then the solution of this is that you say, but this doesn't, this is not a good model then of a real experiment in which we have a little bit of off-diagonal elements.
Exactly, yeah. So I mean, this is a non-unitary equation which has built in an arrow of time. And yet you say, like, where did that come from? And it came from the fact of discarding all these off-diagonal terms. So let me continue and just sort of show a little more about this here. So setting these to 0 is what justifies it, but we can do one step better. We can actually say, well, we can ask what is the time evolution of these, right? So we can actually calculate the time evolution. Instead of just saying, let's assume they're 0, let's assume they're non-zero and then evolve them in time, all right? So you do the same exact expansion, but now instead of n of k, you're asking what is the time evolution of these off-diagonal terms. Perfectly well-defined thing, which you can also do an expansion for. And the answer is quite interesting. It looks like a Boltzmann equation, except that now you can factor out this term. So this is like an exponential type equation, right? And I have a term here which can either be positive or negative. Right? So this plus or minus here is plus for bosons and minus for fermions. So it's very interesting. It says if they're fermions, this overall term is always negative, so that it always dephases. Right? So these terms, these off-diagonal terms, always go to 0 for all fermion systems. On the other hand, for bosons, if you're at low density, then this goes essentially as the square of density, and this goes linear with density in the low density limit. Okay? So this drops off faster than this does. So for bosons at low density, this dominates. All right? And so bosons at low density always dephase also. Right? Which is precisely the Maxwellian assumption to justify the Boltzmann equation. All right? On the other hand, at high density, this term can dominate in non-equilibrium. In which case you have net inphasing, right? You have net increase, right? So if I sort of summarize it here, you have an equation of this form where at low density or for fermions, it's always minus, so that's just exponential decay away. And the time scale is the scattering time. It's the same matrix element squared, right? So it says within one scattering time, your information has been exponentially suppressed, right? So it becomes extremely hard to recover that information if it's every scattering event being suppressed exponentially. So in other words, it's a pretty darn good assumption to say they're 0, even though they're never exactly 0, but they're really, really close to 0, all right? So it's a very stiff equation. If you say, well, I want to keep track of all the phase information that would allow me to reverse time, it's a stiff problem because all the off-diagonal information is constantly being suppressed exponentially fast. On the other hand, as I mentioned with this plus or minus sign, if I have it there, this means that at high density, that your bosons can actually have n-phasing and acquire phase coherence, right? And so this can grow, in which case you'd have exponential expansion or exponential increase, right, of phase coherence. And of course, this is experimental data I showed you, that you see that they are indeed phase coherent. And so this takes us in the whole issue of spontaneous symmetry breaking, because you say, well, to get exponential growth, I have to have this one initially be non-zero, right? So if this is strictly zero, then this is zero always. But if it's oh so tiny, then it will exponentially grow super fast, right? So this is a measure of phase coherence, which is literally exactly what we're measuring experimentally in these polariton experiments, right? So this is a measurable thing, which is the relative coherence between two states, right? So we're just literally doing that with our interferometry. But it only grows if this starts out as non-zero. And how do you get it non-zero to start with? So this goes to a spontaneous symmetry breaking type thing, where this is now exactly for condensate what you often see with magnets, where this is the magnitude of the condensate wave function, and then it's on the complex plane. So we have a phase factor. And so if I start with the system right at this point here, it's unstable toward going down to having a macroscopic condensate with a well-defined phase. But like in spontaneous symmetry breaking, you don't know which one it's going to get, right? Well, you say if there's any little kick here, that will break the symmetry and it'll tell where it ends up. But how do you get that little kick, right? And this is something pointed out by Tony Leggett several years ago. If I have all number and momentum conserving terms, I can never break the symmetry, right? So if you look at this term here, you say, well, what I want is a term like this one. So I want an expectation value of this to be non-zero. So I need scattering processes in which this becomes non-zero for k and 0 different from each other. Well, if I have, say, a two-body scattering, and so I have 2 in, 2 out, that would be all 4 particles here. If these two are not equal to 0, then if these two are equal to each other, okay, then I can't conserve momentum, right? So I can't get a non-zero value of this off-diagonal term with a scattering term that conserves energy and momentum. So something weird is going on. And so lots of ink has been spilled, as they say, over this problem. So one way it was solved, this was a hot debate in like the late 90s, early 2000s, when Ketterle and others did interference patterns of condensates, right? And the question was, well, does the condensate have a phase before you look at it, and then you take the two condensates and they interfere? Or is it that they have an undefined phase, and it's only when you interfere them that they now have a definite phase pattern? Essentially, it was shown that you can't tell the difference. But one way of explaining this, which was widely accepted, was to say, well, actually, what breaks the symmetry to give you the phase coherence is actually measurement. All right, so that if I assume these condensates have an undefined phase, and then I start to leak them out, and the atoms are hitting this detector at the bottom. Every time an atom hits, that's a partial measurement of phase, right? Because the fringe pattern is a phase measurement. And so multiple phase measurements will build up an interference pattern like this, even though number is conserved. So in some sense, that's satisfying, but it just sort of punts it in some ways because we don't know what measurement is, right? So you're kind of saying, well, okay, so what you're saying is some non-unitary term is necessary to get phase coherence, and I can make measurement that non-unitary thing, or something else, right? Yeah.
Well, I think this explanation is very well in agreement with any two complementary observables. Like
Yeah.
you have eigenstate of x, and then you measure p, and then in the measurement there is a p. But once you repeat this, there will be another p. So
Yeah.
once you repeat this again, the phase will be different. Like there will be a phase, but it will be a shifted phase, and from because every run actually is many atoms, and then you repeat many.
So it's also interesting to think about, like, there is differences with the polaritons. We can look at the phase coherence within a single condensate, right? So, like, absolute phase has no meaning, right? Because you have to say relative to what, right? And so in this experiment, it's clear you're saying ground state phase relative to this ground state phase, right? And so the absolute phase of one by itself is almost not meaningful. right?
This relative phase will be
Right, but in the polariton case, we can say I've got a single condensate, and I'm doing the momentum, the coherence that's a function of momentum. So I'm measuring, say, the interference of k and minus k of the same condensate, and we get a well-defined measurable for that, right? And so then you say, well, and that's leaking out continuously. Like, how does it know to find a definite phase? And some people would say, well, because it's leaking out, that's a measurement. And so that basically already, collapses it. But again, you're introducing a non-unitary thing somewhere along the way in order to get coherence. So this is just a little detail. Do you guys mind if I go longer? And this is just the last thing. Weirdly, this term which we calculated can become very important out of equilibrium, but in equilibrium, this doesn't go to 0, it goes to slightly negative, all right? And you can just show one line that every one of these terms becomes slightly negative in equilibrium. So when you're out of equilibrium, the inflow to the ground state becomes dominant. But at some point, it stops because you're in equilibrium. And then this term here is ever so slightly bigger, which means the thing is always slightly dephasing. But condensates don't dephase, they're good phase coherence. So how do we get them to stay coherent if I've got a term that says it's always slightly dephasing? And that's an open question. So I just threw out this very analogous to what I talked about in my first talk with number operators. Maybe for bosons, there's an analogous non-unitary thing, which would favor going toward coherent states and give you this extra little kick. And it gets back to, again, sort of philosophy side of things to say, well, you can show that measurement gives this type of thing, right? So could you reverse it and say this type of thing gives measurement, right? Or are they really just two sides of the same coin? All right, I'm going to skip that and just go to my conclusions and leave it at that. The ring traps are just a lot of fun because they're nice and stable at this point. But I am looking for theory collaborators to talk about the momentum. The data we have is under-analyzed at this point. Like, we have data that's very clean, that doesn't fit any of the textbook theory at this point. And I will also just invite you all to visit Pittsburgh anytime. I'm also always looking for postdocs and graduate students, so feel free to contact me or put other people in touch with me. But actually, the weather's pretty similar to Vienna, so I can't say how, it's actually, from what I've seen, it's about the same. You get your gray days, you get your sunny days, you have your mountains. We don't have any Alps near, though. Okay, so I'll finish with that. Thanks.
Maybe I just can start because it's a follow-up on this discussion that you mentioned that was in the community, whether the DC has this definite phase even. I would reformulate maybe the question whether the DC has a definite phase before the measurement and the number. And then one way to attack this is what Frank Ladoy did, and he considered two entangled DCs. And then having both them well defined is nothing then else than introducing hidden variables for two non-commuting observables in a sense.
So he did not introduce hidden variables, or he did?
No, he said that this statement that the phase is well defined and the number state is also well defined is actually assuming a hidden variable in quantum mechanics.
Yeah,
it could be the case, yeah. And then he just ran the Bell experiment in a sense, theoretically. And showed that if this were the case and these hidden variables were local, then they could not explain correlations between.
No, local hidden variables is experimentally disproven. So non-local hidden variables is another issue.
I think his merit of his work was to identify this question, which as a question about hidden variables. Once you do it, then it's easy to disprove. But and so one could say that this phase was not there locally before the measurement was performed. Because if it were there, and it would be hidden there.
Yeah, there's weird things though in that, like the interference pattern I showed with the ring circulating left and right. Like you can tell, like if you've got a condensate and you're saying it's in a superposition of all possible phases until somebody looks at it, like that is physically different from one that has a definite phase, which I just don't know, right? And so, like thermodynamics comes in because, like, you know, if I go to that sort of standard picture of symmetry breaking, like, oops, I guess I'm not broadcasting here. Like saying that it's in definitely here is physically different from saying it's in a superposition of all of them, right? And there are tests one could do.
In the quantum theory, but Frank Lloyd is saying, okay, even if you measure the superposition, you may think that there is some hidden variable that if you had measured instead of superposition in the basis or phases, there would be a definite phase. And this can be also excluded.
Yeah, so one of the things that makes phase different from other things is that phase is intrinsically a relative measurement, right? So like if you think about like position and momentum, you could say like, I could say, here's the momentum of this, and it is what it is. If I don't have to know that, you know, well, I guess you could say relativity kind of, you know. But with phase, some questions are just ill-defined if you want to say what is the absolute phase, right? On the other hand, as I was saying, like, I'm not sure the same type of thinking has been applied to, say, if I have a single condensate and I ask between two different K states within that single condensate, now that's a well-defined problem, which is an experimental measurable for us in polaritons. And what theory predicts what that will be? And does that answer, so, you know, it's basically, you know, what we are measuring, you know, is, that's a well-defined measurable. And does that need measurement to have an exact value? Or could that have a meaning even if nobody looks at it? I don't know the answer to that question. So you think his argument would apply to that too? Yeah, because I'd like to see that paper then. Yeah.
A couple of things. First of all, just a small comment, which is that, you know, you say the question of is the phase exactly here or is it in a superposition of all positions? Of course, that's even that is a different question to the question of is the phase at the top of the hump, right? That's a different position for it to be entirely. So that's
Yeah.
That's a different thing to consider. But the main thing I want to say is if you go to the second of the two open questions.
If I get what?
If you go to the slide with the second of the two open questions, I guess.
Yeah, this one here.
Yeah. So one thing I'd like to ask is, have you looked at what happens for the fourth order term, the time derivative of
We did actually, the short answer is that there's nothing in perturbation theory that will help solve this problem, right? Yeah, you can go to like, you know, three body scattering and things like that, and you know, it's always hard in perturbation theory to say you have accounted for all the terms, like, because there's always an infinite number more. But there's nothing that leads me to believe that just adding more terms from perturbation theory would change the overall picture of this. So I mean, the interesting thing about this is a new result. Again, so under all the same assumptions of two-body scattering or thermalization that one would typically make to generate the Boltzmann equation, right? This is as equally rigorous, and it says there's always actually an intrinsic slight dephasing of every Bose condensate. And I don't think that, I mean, it's a new result, so that hasn't been widely thought about in the literature.
Okay, thanks.
Mm-hmm.
Yeah, very interesting. Thank you. I have two questions. One is kind of related to the last, which is that if we think about equilibrium, we're thinking about the infinite time limit somehow.
Mm-hmm.
And it seems to me, at least a priori, that would be in tension with perturbation theory because, I mean, if you take the Hamiltonian and multiply it, it's, you know, if you could solve the problem exactly, it would be e to the IHT, right? Where h is your total Hamiltonian.
Mm-hmm.
And as t is going to infinity, if you can separate your h out into various terms of different magnitudes, let's say, or the different sort of small prefactors, then as t goes to infinity, the difference between them becomes less important. In fact, this is relevant for this phenomenon that you can kind of vaguely still see this squiggly graph that I drew.
Right, yeah.
Pre-thermalization. The point there, in fact, is that you have the term that's kind of
Mhm.
negligible. But in the infinite time limit, that term can become just as important as the other term. So I'm curious if one could perhaps see deviations in the equilibrium statistics by the inclusion of later terms. I mean, yeah, you mentioned that you
Well, so what you mean by fluctuations can be different for different. So, like in this calculation, you could calculate like the expectation value of n squared, for example, right? But you would not get anything that was actually fluctuating in time. You would just see that the value of n squared had some deterministic evolution, right? So you could, so you could certainly do this, right, as a calculation and say, what is that? And that would be a well-defined thing, all right? From that, you basically would get a smearing of nk, to say what is the variance, okay? But this would be also a deterministic thing which would evolve, right? So you would never see anything in your actual calculation fluctuating because you're already kind of fixing the problem to not see those.
Right, but what I meant by deviation, it was more sort of in the equilibrium distribution, that perhaps by the inclusion of more terms, one might find sort of the first
Well, okay, so
terms giving the Maxwell-Boltzmann, and then
in the calculation we're doing, we're assuming a spatially homogeneous gas that's not homogeneous in momentum space, but it's homogeneous in real space, and it's infinite and it's closed, which means there's no external reservoir, but it's still infinite. Under those assumptions, like everything, there's nothing that can give a time-varying fluctuation, right? Because every point is translationally invariant to every other, right? So every place at any given time, every point looks exactly like every other point. So you can't get a fluctuation in time in such a situation. Now you could say, of course, we sort of forced it to be that way. And suppose I started with a thing that had spatial homogeneity, then presumably I would see those things wiggle. And my analogy to that would be like if I throw a pebble into a pond and I see rings traveling out, they will go out deterministically, right? If the puddle is finite and energy conserving, then all those waves will bounce off my borders and come back and at some really late time create a new set of rings. If it's an infinite pond, they just go out forever and eventually it never comes back, right? And that's the Poincare cycle going to infinity. Okay? I did want to maybe pull up one thing real quickly though, because I think it relates to some of the questions you're asking. Oh, I was wondering why I couldn't see this here. All right. I'm going to pull this up real quickly. It's a somewhat helpful diagram. All right, so if I go down here. Yeah, here it is. All right, so this is the way I think about it. I can say, all right, so suppose state 1 is a pure Fock state, all right? Now we would say the physics is that it goes to state 2, like the actual unitary physics, all right? And on the other hand, we're saying that this is extremely close to what is found by a Boltzmann equation, all right? So the Boltzmann equation finds state 2 prime, all right? And it's a very good approximation to what this is, okay? Except that here, these off-diagonal terms are oh so close to 0, but not quite 0. And this is strictly 0, all right? So now if I was to take this and run unitary evolution the opposite way, I would get back to state 1, right? Which is the same as saying if I ran state 1 backwards, I would get to state 2 in either direction, right? On the other hand, if I'm at state 2 prime, which is the approximation, okay, it always goes to this direction. So this is a good approximation. So if I run this forward, I get state 3. And state 3 prime is a good approximation of 3, just as state 2 prime is of 2. So if I'm running time forward, then the Boltzmann equation is always a good approximation, okay? On the other hand, if I run it backwards, okay, state 2 prime does not go to state 1, right? It goes to state 3 prime, right? So that, essentially, you can see that, it always works this way, but you can't run it backwards in the same way that you could a true unitary evolution. Well, maybe we should call it a day, huh? Okay. All right, thanks. Yeah, should we chat over lunch, maybe?
Or chat for lunch.
Yeah, why don't we just, I don't think we need to draw so much.
I can also bring something to write down.
Need a pen and paper or something, sure.
I realized I answered my own question with this extra terms of the perturbation theory thing. If they don't contain extra symmetries, then they can only,
exactly.
By entry maximization, they can only result in mass.
Yeah.
So
And
if you have some symmetric terms, but they come in some order, that's the only circumstance.
yeah, well, the other thing is that generally, if the higher terms are important,